So we're live now.
Hi and good evening. Welcome to the CIBSE HVAC Group Annual General Meeting. So for those of you who don't know me, I'm Mary-Anne Clark. I'm the chair of the HVAC Group. I've been in the position now for just over a year. And this meeting is an opportunity for you to hear about all the good work that we've been doing over the last year. So we obviously want the next couple of hours to be interesting and informative. So we've lined up some great speakers on the topic of electrification of heat and load management. So we're really hoping that you're going to stay on for that. I personally can't actually get over the speed that the industry is changing and moving towards electric solutions with new and evolving technologies. They seem to just be coming out all the time. And obviously, as an industry, we really do need to keep pushing towards net zero, researching, investigating, failing. Yes, sometimes we fail, innovating and learning from each other, which is why I'm so pleased that you can be here today. Please do note that this meeting is being recorded and that we will be issuing CPD certificates. So feel free to post questions for the group in the chat box as we go along. So our agenda for this evening, introductions to our group, our mission, introductions to the team members, future group events and our strategy going forward, summary of our previous events from last year, contributions to publications, other business, and then close out. And then obviously we have our electrification of heat and load management coming up at the end. So what is our mission? You may or may not know we launched in November 2017 and our mission is to support and encourage the efficient design and installation and operation of heating, ventilation and air conditioning systems. We have a number of objectives as a team. I won't go through all these in detail, but obviously if you are interested, information can be found on the CIBSE website and that will go through the details there. We believe our scope covers a broad range of components and interfaces. They all feed into heating, ventilation and air conditioning. And the whole idea is that our systems create healthy, safe and sustainable buildings for all. So this is the team. I'm sure there's lots of names there that you will recognise, and it's made up of a fantastic range of people from different backgrounds and companies, so that we hope we offer a diverse group of opinions across the building sector. A lot of our members are well known across the industry, but we also have up and coming engineers with new ideas and innovations. So that's great to hear some of the views that they have. We are in the process of creating some bios for each of our team members so that you can find out a little bit more about us, and these will be posted on our group website. So as you can see, we have the maximum of 12 voting members and we have 10 co-opted members. And we also have, oh, apologies, my son's just come in, but he's gone now. This is what happens these days. So we also have an events coordinator, Matt Dickinson, who really helps with some of the events going forward. And we currently have no objections to this list. So for your information, we have 1,180 subscribers and they are split between CIBSE members and non-CIBSE members as shown here. We always like to welcome new team members, so do feel free to contact anybody on this list if you wish to contribute to the HVAC specialist group. And as a group, we try and meet quarterly to discuss hot topics, organise our next events. And I'm actually now going to pass over to Phil, who's our vice chair, and he's going to give you an overview of our event strategy and future presentations that will be available. Phil, over to you.
Thank you very much.
As a group, our aim is to host 4 events a year to help improve the industry as a whole, the knowledge, application, and where possible, provide case studies on relevant subjects around heating, ventilating, and air conditioning. We try not to plan more than 12 months in advance to ensure we could talk about subjects that are relevant, but also to ensure we can get the right speakers to give the broad range of information and to form a good snapshot and to give subject matter experts consideration around the required subjects. Due to our range of members, it allows us to consider and give information in a way and output that would be informative from all angles, looking on the client side, designers, installers, and manufacturers. This structure is to help allow and give other considerations and requirements to be viewed and understood. We have a number of events planned for the year, from tonight's events covering storage considerations for HVAC, both thermally and electrically, to help provide solutions for current issues around net zero design. On the 18th of May, we'll be covering Part O, and the effect of overheating on properties and how it's considered for design and operation. This event will be looking to make hybrids, and it'll be our first event for nearly 2 years in person. For our late summer events, looking for September 14th, we'll be looking to cover embodied carbon. We'll be hearing from clients to understand their needs, from manufacturers to give understanding of what they're doing to try and look to reduce it, and line up some influential and knowledgeable speakers to help upskill the industry. Finally, for our last event for the year, we plan to do an event around the building safety bill. As part of CIBSE, we are totally committed to work with our members, and we feel that an event to give an understanding of what the bill and how it will affect the UK and specifically the HVAC systems, along with related requirements to reduce carbon emissions for the existing building stock and address the need for improved indoor air quality, in particular air quality for our buildings in the future. Thank you.
Thanks, Phil. And we're now going to pass over to Matt, who's going to tell us about the events that we've had in the last year.
Yep, so hi everyone, I'm Matt and I help coordinate events for the HVAC group. We've had 4 amazing events this year, and it's my understanding that actually as a group across all of our events, we've had the most attendees out of all the various special interest groups, so that's fantastic to hear. As Phil mentioned, we've got lots more events planned for the upcoming months, but if you do have any topic suggestions or if you want to get involved, then please do email us or get in contact with one of the people in the committee. We started off the year last year strong with an event on the ongoing management of COVID, and that actually the recording of that video on the CIBSE's YouTube page is one of their most viewed videos, which is great to see. We then followed that up with 2 joint events, one in May with the Energy Performance Group discussing hydrogen and its future role within our energy mix. And then in September, we had a panel event discussing innovation in building services that was held jointly with the FM Group and with the Young Energy Performance Group. Then in December, capping off the year, we had an event on tackling indoor air quality, and hopefully most of you are here now to stay to watch our event after this session on peak load management. Hopefully some of you will have seen that we made it into the CIBSE Journal this year this month for this event, and we're hoping to keep growing our followers on LinkedIn to try and advertise these events a bit more. But it's been a great year, and hopefully the next year will be just as good in terms of our events. Thanks.
Thanks, Matt. So as a group, we have made a number of contributions to publications over the year. I'm hoping that we've got Chris on the line. I don't know if he's made it. Oh, fantastic, Chris. So I just wanted to pass over to a couple of our group members who are going to tell us a little bit more about what we've contributed and where. So over to you, Chris. Thank you.
Hi, thank you. Collectively within the group, we've got considerable experience and knowledge. Marianne mentioned the way things are so rapidly moving so quickly within as we respond to climate change. And as a result, we're called upon within wider CIBSE to contribute to a lot of publications. And indeed, what is the interesting thing is a lot of us contribute to these things. It's a two-way process. We're learning just as we're contributing. AM17 which I'm going to major on now, is guidance for large heat pump installations. It's got funding from BEIS. It's seen as a very high priority at a government level, and we're seeking to fill gaps in the market knowledge and be able to disseminate to the wider industry. This follows on from AM16, which was looking at large multi-residential heat pump installations, and we can see some further publications likely to be needed as well to try and fill the gaps. But as a snapshot, I now hand over to Tony.
Hello, I'm Tony Day, and I've been involved in a couple of the publications in the last year. We were invited, the group was invited to contribute to the COVID-19 ventilation guidance. There were 4 versions of that put out last year. It was a highly sought after document, viewed many times, downloaded many times. I think probably one of the largest downloads of CIBSE guidance, and that was put together by a relatively small team, and driven very much by the natural ventilation group as well. But there were other people who were involved around SAGE and other government advice. So that was a very important piece of work. Another piece that several members of our committee, the HVAC Systems Committee, were involved in was TM67, and that's the electrification of buildings for net zero. I'm going to touch a little bit on that tonight's event is kind of an offshoot of some of that work. I was chair of that working group, but there were a lot of contributors from across industry, and again that had a launch in November with a very large online attendance. So this is we think important work and important contributions, and then there are a number of CIBSE journal articles, and I think Marianne, you're going to talk about those.
Yeah, no, thanks, Tony, and thanks, Chris. Yeah, so obviously we've been doing some fantastic work with publications. We do try and get into CIBSE journals. I don't think Matt mentioned it, but what we try and do is once we've done an event, so for example, today, we will try and write that up and give a bit of a summary, so it gives our members an idea of what the content is for our events, and then hopefully that encourages you to come to our next event. That's the plan anyway. So hopefully you find them useful, and obviously any feedback is worth having. So thanks for that, guys. Right, just moving on. Okay, so other things that as a group that we have been working on, we've been doing peer reviews on training modules. Here are some of the ones that we have worked on. So design of ductwork, heating systems and air conditioning systems. So we feel as a team it's really important that we are helping to review these modules to make sure when they go out into the world that someone has done a check on them. Another thing that we just wanted to mention to you tonight was that we are awaiting a new fresh looked CIBSE website, which is coming soon to a device near you. CIBSE put a lot of effort into this, and we will have, so each of the groups will have their own pages or links, and so you will be able to go to the HVAC group page, and you will be able to download the events that we've been doing, any publications that we've done, have a look at our objectives, and if you want to get involved you can go through that as well. So I think it's a really fantastic opportunity for us to connect in better with our members. I think there might be a place where we can have sort of a Twitter, or if we've got any ideas, sort of a snapshot of things to put in there. So that should be quite quite nice to see, moving with the times. So that's great that CIBSE have done that. And obviously, before we just move on to the main event, I don't know if we've had any questions from the audience. I can't actually see from my screenshot, so I will ask Phil or Matt if there's any questions that have come up.
None at the moment.
No, okay. Please do pop in any questions. If we don't get any questions, we might just have a couple of minutes break before we transfer over to our guest speakers. But I suppose I would just like to take this opportunity to thank everyone in the team and the members that support us, that continue to support us and contribute over the year. Obviously, it's a little bit tricky doing these events online because you never know sort of who's there and what the feedback is. So hopefully moving forward, we will get back to a state where we have at least a hybrid situation, so we can get a little bit of feedback, because obviously it's sometimes difficult to gauge the audience when you can't see or hear them. So Matt, have any questions come through just while I was talking there?
No.
No, lovely. Okay, well, what we'll do, I'm just going to, are we happy to just move on straight onto the next group? Have we got all our speakers here? I suppose
Yeah.
need to check.
Yeah, that they're all here and ready.
Is everyone ready to go?
I think so.
Lovely. Well, let's just plough on. So obviously, we wanted to do a presentation here. So the inspiration for this event has actually come from several committee members who you will have heard from and are part of the working group. And they recently published the TM67, and that focuses on electrification of buildings for net zero. Obviously, there are many environmental benefits for electrification, but the widespread adoption of electric heat has also presented some challenges. And one such challenge that is that the committee have identified is a key issue to address. And that is how to manage the electrical load on the energy grid. It is rapidly becoming clear that we must manage peak loads into the energy grid to ensure its stability. Energy storage of varying kinds is going to become essential in ensuring a successful project. And our presenters today are going to discuss the different types of storage to consider, both mechanical and electrical. And we will finish with some questions and answers, so please do pop them into the question box while the presentation is going on. So we have some fantastic speakers for you today. I will introduce each one as we go along, and to kick off the event, we're going to pass over to Tony again, Tony Day, and he was the chair of the working group for the TM67. He's currently an independent consulting specialist in low carbon solutions and is an active member of the HVAC group. And if you don't know Tony, then you need to know who he is, and here he is now.
Excellent, thank you very much. So I will share my screen. And I want to, oops, sorry, I need to stop sharing that screen. You don't want to be seeing that, so so I want to share my presentation. So can you see that that presentation screen?
Yeah, we can see that if you put it onto presentation mode.
Go. Here we are.
There we go, perfect.
So electrification of heat and load management. So as Marianne says, this has been really, I suppose, a spin out from TM67, which took about 18 months, I think, in total to produce, which actually was a very fast track. Started with the CIBSE Knowledge Generation Panel asking for ideas, and this is one that came to the fore. We were able to assemble a really good working group very quickly and write something by committee. I was the editor for that. There were a lot of really good contributions. So the key issues that really came out of this, it's a high level document. It's really looking at a lot of the questions, a lot of the issues that we need to consider rather than giving all the answers. And as Chris said earlier on, with AM17 coming forward, there's going to be more around heat pump design, and there'll be more about storage design, and we've identified a lot of areas that need to be looked at in future for further guidance. But so what were the key issues? Well, the electricity system has rapidly decarbonised, and therefore heat pumps have become the current choice for low carbon heat if we're going to do this quickly, which we need to do. And distributed generation is increasing, and that's increasing the local electricity flows on the network. And EV charging is now being added to the building loads and obviously to local networks. And so all of that is actually combining to give a new set of challenges, not just to the building services engineers, but to the interface with the grid. And energy storage may be just one of the answers to help us with controlling those issues of peak demand and cost management. And I think another thing about this is that energy markets are evolving as the transition accelerates, and by that I think pricing is going to become all important for how we encourage people to shift their loads and to take up new technologies for that. So this is just a quick snapshot of the carbon intensity on the UK electricity network, and you can see from 2013 to 2020, that's been, I think it's a 65% reduction in carbon intensity, and that's probably happened faster than many of us expected and anticipated, and probably faster than the network was anticipating as well. Hence now the real focus on electrification of buildings and the opportunities for decarbonisation that presents. But here's one of the challenges: is that the red line there, the electricity, the UK or GB electricity demand, and this was in 2017-18 winter, and we can see that the peak electricity demand on the grid is around 50 gigawatts. But if you look at the peak draw on the gas grid, that's the equivalent of up to 200 gigawatts. And even the average, that's the peak load, but even the average conditions, and that's a typical day, is certainly significantly more, perhaps 3 times more than the demand on the electricity grid. If you were to transfer all of that load from the gas grid onto the electricity grid, we would have a significant challenge, even if you've got heat pumps with COPs up to 3. You'd still be doubling that demand on the grid, theoretically. Of course, it's going to happen much more rapidly. That's not going to happen in one big lump. It's going to happen gradually and piecemeal, but nevertheless needs to be managed. And the other issue of this is the ramp rate. So gas, the uplift, so the 3-hour uplift in the morning on the gas grid can actually, can get up to 100 gigawatts, 110, almost 120 gigawatts within 3 hours, and that's a really fast ramp rate, whereas the electricity grid probably sees ramp rates maxing out at around 15 gigawatts. So that speed at which the demand comes on is also going to be critical, I think, for grid management. And this is not just a national issue, because this is going to be variable around the country to different load points. So different substations will have different amounts of capacity and additional headroom that they can have, that they can supply, both for supply of generation of renewably generated embedded generation, and also for demand. Those two headrooms are obviously sometimes different for different substations. So this could be right down to the local level about what we're going to do in terms of load management. And that means building service engineers are going to have a better understanding of what's going on in the local grid. And others tonight may present similar drafts to this, but this is what's going on. The electrified home, where this is a house that was being monitored in Ireland with 10 kilowatt hour battery, rooftop PV, air source heat pump, EV charging. The blue line is the demand from the grid. The green is is energy into the battery. You can see that the purple line over that is the state of charge of the battery and how that changes over time. And there's some PV contribution in there, and we can see that the discharge from the battery is where the load shifting is happening into the peak times. And this is aggregated data from about 20 different houses. And again, it's the same sort of information, but what we're going to get with lots of properties, lots of connections that see all of these different energy flows that we're going to have to manage. And that's really tonight what I think we'd like to explore about how some of this is going to be taken forward. And it's not just about electricity storage, but also thermal storage has a part to play. This is a very idealized graph of a heat pump operating without any storage, and a heat pump theoretically operating with storage to completely flatten the load on the grid, so you have something much more reliable. So thermal storage is going to have a significant part to play in the electricity load management as well. So that's all I really want to say. It's just really to introduce the subject and some of the headline issues that we'll be talking about. So thanks for listening, and now I'll pass back to Marianne. Thank you.
Thank you very much, Tony. That's a great introduction to the topic. So next up is Dr. Daniel Mahon. Daniel is currently a researcher at the Centre for Renewable Energy Systems at Loughborough University. His research has been focused on thermal storage, including industrial and domestic applications. Thank you, Daniel.
Hello. Okay, yeah, so I'm Daniel, as introduced. So basically what I'm going to be talking about today is I'm going to give a quick introduction into thermal energy storage and hopefully explain how these systems potentially can mitigate peak grid loads. Okay, so just very quickly, in a nutshell, although Tony did a good job of explaining it previously, these are some key figures. So around 29% of the UK's total energy consumption is used specifically for domestic space heating and domestic hot water. And 70% of the energy for domestic space heating and domestic hot water currently comes from gas and oil, which means around 20% of the total UK's energy consumption is from gas and oil, specifically for domestic space heating and domestic hot water. And obviously we're getting an increasing amount of intermittent renewables on the grid, which generate electricity, not heat directly. And we can't guarantee that the renewable energy production will coincide with peak grid demands. So basically we need storage. We need to reduce the grid peak demands and utilise this renewable generation. But we also need a way to turn this electrical energy into heat for domestic space heating and domestic hot water. So I'm going to spend the rest of this presentation talking about how we can do this, potentially with thermal energy storage. So basically thermal energy storage is just the storage of heat for use at a later time. We're all familiar with electrochemical batteries. They store electricity and they output electricity for use at a later date. This is essentially what thermal energy storage does. It stores heat, not necessarily directly as heat, but then it outputs energy as heat. Most thermal energy storage systems are very flexible, so they can be charged or they can store energy directly from electrical resistive heating, but they can also be charged by heat pumps or solar thermal technologies, for example. And they can normally have multiple energy inputs as well at any one time. And they're normally broken down into 3 different technologies. So you have sensible, latent thermal energy storage, or PTM, and then finally thermochemical. And obviously, depending on your application, a different thermal energy storage technology will be more or less advantageous. So the first one, the most simple one, is sensible thermal energy storage. So this is essentially just heating up a material, taking advantage of the specific heat capacity, insulating it, storing it hot, just like we do with a domestic hot water tank. And then we, to extract the heat, obviously the system cools down, and then we output the heat for our baths or showers or around our radiators. And to just put a figure on that, the energy density of water with a temperature difference of around 25 degrees C typically has an energy density of around 105 joules per gram or 29 kilowatt hours per cubic meter. So the advantages of a sensible storage system is it's a developed technology. Domestic hot water tanks have been around for decades. It's relatively cost effective. The storage tank itself doesn't cost much, and obviously water is a very low cost storage medium. The power outputs can actually be quite high if the heat exchangers are designed correctly, and also they can be used for long-term, large-scale storage. Not in a domestic dwelling, but they can be. You can have large stratified water tanks, which could then be potentially connected to a district heating network, which can then source domestic dwellings for heating purposes. The energy storage efficiency can also be high. As long as you charge and discharge within a suitably small period of time, then you can get most of the energy out which you put into the system, and it's just a function of the heat losses from the system. That's also a disadvantage because obviously we all know our water tanks over time lose heat and therefore lose energy. So they're only really suitable for short-term energy storage, a maximum of around a day. And the energy density is relatively low, around 29 kilowatt hours per cubic meter. So the next type is latent thermal energy storage. So this takes advantage of the energy involved in the phase transition of a material. So when we're talking about phase change or latent heat for domestic use, typically the material can be a wax. So you take a solid wax material, you heat up the wax, and then when the wax transitions from a solid to a liquid, it absorbs quite a large amount of energy over a relatively small temperature range. So it can store around 200, typically around 200 joules per gram of energy over a 1 or 2 degrees C temperature range, which is around double that of what a domestic hot water tank can store over its entire temperature range. Another advantage of a PTM system is the storage periods can be longer. So not very long storage, but around 1 to 2 days typically, so around double that of a hot water tank. The power outputs can be large, and they're also, because the phase transition is only over a very small temperature range, you can get quite large power outputs over a small temperature band, which makes it ideal for instant hot water. The disadvantages though, there are some technical difficulties, so optimizing the charging and discharging of heat transfer. So the phase change materials don't tend to have great thermal conductivity, so you have to develop large heat transfers with specific heat exchangers. There are also energy losses with time, just like a hot water tank, and there are minimal systems on the market. I think Toby from Sunamp is going to speak to that system next. And finally, the final type of thermal energy storage is thermochemical. So this takes advantage of the enthalpy involved in reversible chemical reactions. So typically, when we're talking about it for a domestic environment, we're talking about a gas-solid reaction. So you have a solid thermochemical material, and the gas is just normally air with a water content. So to charge your thermochemical material, you just heat it up, which removes all the moisture, and then you store your thermochemical material dry, and then to discharge and release the heat, you just add water, it's absorbed by the solid material, and then you get an output of heat. So the advantage of thermochemical is mainly its energy density. So you can have an energy density around 10 times that in a domestic hot water tank. So you can have a very energy dense, compact energy storage system, and long-term energy storage. So typically for a thermochemical material, around 80 to 85% of the energy is stored as chemical potential energy. So you only lose 20% of energy as sensible heat. And this chemical potential energy can be stored indefinitely as long as there's no side reactions, which gives rise to seasonal thermal energy storage. So you can charge the chemical material in the summer when obviously the supply is high and demand is low. Store your chemical material, store 80% of the input summer energy until the winter months, and then discharge the system obviously when demand is high and supply is low. The disadvantages are it's predominantly still in its R&D phase, and cycle stability are problematic. So now I'm going to talk to you about actual systems or some data on the 3 different thermal energy storage technologies. So this is the Mixergy Smart Sensible Thermal Energy Storage System. So it's basically a domestic hot water tank. They're available to buy, they're rolled out across the UK, there's quite a lot of them available. They're very flexible, they can be charged by a range of different sources. And it's basically a volumetric heating system, so you're only heat up or charge the amount of water which you need. And they announced in 2021 they have a frequency response of around 1 megawatt. So all of these systems rolled out across the UK have a frequency response of around 1 megawatt. These next two slides are directly from Mixergen, just give you a bit more of information about how the system works. So this top image here shows how the mixer system is charged, and basically it has an inlet diffuser in the bottom. So when the cold water enters the hot water tank, it reduces the mixing, which means there's more available hot water in the system. Whereas with a conventional hot water tank, as the cold water comes in, you get much more mixing and then you get less usable hot water in the system. And also, because this is a smart system, it's connected to an app, it's connected to a cloud, and it has machine learning too. So this graph here shows how the hot water tank is charged with time, with and without machine learning. So the red plot is without machine learning and the blue plot is with machine learning. And basically what happened is the system realized it's good to charge between off-peak hours, so between 3 and 6 PM with low-cost electricity, and then also it only needs to be at around 45% capacity for the rest of the day. So with machine learning, it shifted the peak charging to off-peak periods, and it resulted in a reduction in the water bill, so from £135 to £80 per year. Okay, so this is a phase change system which we developed at Crest. So this is a CAD image of the system, but we actually built it and tested it, experimentally tested it, and it had an energy density of around 54 to 56 kilowatt hours per cubic meter. It's charged between 60 and 70 degrees C. So this is an ideal temperature, although slightly on the upper end of what heat pumps can achieve, so it could be charged with a heat pump. And the phase change temperature was 42 to 43 degrees C. So this is this very small phase transition temperature when it goes from a solid to a liquid. And over this 2-degree temperature range, it's stored 218 joules per gram. So double the amount of energy can be stored in this PCM system over a 2-degree C temperature range and can be stored in the whole temperature range of a hot water tank. When the system was scaled to 10 kilowatt hours, you can have a peak input power around 30 kilowatts and a power output after 10 minutes of around 10 kilowatts. Now these are the peak numbers. They're very flexible, but it just shows the sort of capacity, the power capacity you can have with these systems, although you don't need to charge it with 30 kilowatts. And I'm just going to talk quickly about some published experimental research on some thermochemical materials. So this thermochemical material was developed for domestic use, again at Crest. It had a charging temperature of 150 degrees C, so higher than what a heat pump can achieve, but with direct electrical resistive heating, you can probably get to 150 degrees C. It had a specific energy density around 700 joules per gram, which is over 6 times greater than the energy density of a traditional hot water tank. A peak power output of 30 kilowatts. Again, this can be scaled down. 30 kilowatts is probably higher than what a domestic dwelling needs. And it has a performance of 85%. So this 85% performance is the chemical potential. So you can, of your input energy, you can store 85% of the energy as chemical potential without any losses. So this is the potential for seasonal energy storage. 85% can be stored seasonally or even longer. And a charging input power of 64 kilowatts. Again, this is the maximum, but this is the capacity a system like this could have. And then very quickly, this is some information from a feasibility study, which was again conducted at Crest. I'm not going to speak too much to the schematic, but this just gives an example of how a thermochemical with a solar thermal collector system could be integrated into a household. So basically, the feasibility study looked at a thermochemical system being charged by a rooftop solar thermal collector over the 3 months of summer, and then it was discharged over the 3 months of winter. So there's only one charge cycle per year, but there could be more. And the cost for storage worked out for the best case system we tested was around 5.1 pence per kilowatt hour. And the yearly energy production from the system was around 4,500 kilowatt hours per year. And it was with a vacuum flat plate collector, something which there aren't many commercially available at the moment, but it's another part of research we're developing at Crest. Yeah, so that's everything from me. So the purpose of this presentation was to give an outline of the different thermal energy storage technologies and how they potentially could be applicable for different grid peak shifting activities.
Thank you, Daniel. Really informative. I'm sure there's going to be a few questions a bit later, so we will pose them to you at a later stage. So now it's time for Toby Morris, who is a specification manager for Sunamp. He has over 15 years experience focusing on delivering net zero carbon solutions through the use of phase change materials. Over to you, Toby.
Thank you very much.
We can see your slides there.
Right, there we go. Sorry, wouldn't work. I'm assuming you can hear me now.
Yeah, we can hear you. Do you want to just put it on full screen? Yeah, perfect. Lovely. Thank you.
Great. Yeah, so thank you very much for having me. I'm Toby Morris, working with Sunamp, and we actually have developed our own phase change material thermal storage units using our own developed material called Plentygrade. And I'll be talking about some of the applications of phase change materials and how important thermal storage, but also phase change material based thermal storage will be to this transition. I don't have very long, so I'll just go through some of the case studies at a very high level, and obviously we'll have a bit of a Q&A afterwards. Just wanted to pick out a couple of things from the technical memorandum that Tony talked us through briefly earlier. One, obviously, the UK peak heat demand is between 3 and 4 times the peak winter electricity demand on the gas grid. Even with high heat pump coefficient performance, this represents a really significant shift, and it's going to result in a huge financial implication in terms of facilitating that transition due to the grid upgrades that are going to be required. So demand reduction and energy efficiency are going to play a crucial role. And also, it's important to note that those electrical network upgrades or the costs of that will ultimately be borne both directly and indirectly by the end users. So at a building level, we're going to need to play a much more active role in balancing the electrical grid. So thermal storage is going to play a huge part in facilitating this transition. It's not going to be taking the entire load for sure, but it's going to play a significant role. Tony obviously showed this earlier, and I thought it was just important to highlight that significant step change that's going to be taking place if we have this transition. So using thermal storage, there's 3 pivotal points which the thermal storage will impact upon. It's going to reduce the export of renewable energy that's generated, and so that we can use it internally. That's going to have benefits in terms of reducing the demand on the grid, which will be important. It's going to have obviously reduced CO2 emissions and reducing running costs. The other side of it is that we want to try and decouple the electrical demand from the heating or cooling and the hot water demand as much as possible. So we're going to, the thermal storage will enable that load shifting to facilitate that and reduce those peak demands. And again, that's going to reduce the demand on the grid, potentially reduce the size of these central plants that may be required, and increase overall efficiency. It avoids peak tariffs and reduces running costs again. And the other side of phase change materials, particularly in terms of thermal storage, is the energy density that Daniel mentioned. The energy density of the phase change material being so high means that we can provide very compact storage using phase change materials. And that really will mitigate a lot of the space constraints which are there today, but will only be emphasised by the fact that thermal storage is going to be required a lot more going forward, and therefore, mitigating those space implications will be really important. So, phase change materials, we at Sunamp have actually developed our own, known as Plentygrade. It's sodium acetate, so it's salt and vinegar based. It's actually a food grade material. And just this is a particular material that we developed that called Plentygrade 58. so named because it changes phase at precisely 58 degrees. And that's really important. You can see some of the, on the right there, challenges of existing PCMs. Part of the process for Sunamp has been overcoming those challenges. And we've done that with the Plentigrade that we developed. So looking at this particular example of Plentigrade 58, just gives a very clear illustration of the process that's happening inside the thermal storage unit. We have a blue line here, which is your typical water storage. And as we've got energy density on the y-axis, and temperature on the x-axis. With the water, as we put energy into it, it correspondingly increases in temperature. Now, the phase change material, or in this case Plentigrade, is in a solid state initially and will act in much the same way until it gets to what we call the critical temperature, which is the phase change temperature. That's the melting point. And you'll see at 58 degrees it starts to melt. As soon as it starts to melt, instead of increasing in temperature as we continue to put energy in, it actually just starts to absorb all of that energy. And it will continue to absorb and absorb and absorb until it's fully melted, at which point it's effectively fully charged. It can't store any more energy. So at that point, if you continue to put more energy in, then it would increase in temperature. But what it shows us, but this temperature range for this particular material, once we've triggered that phase change process, we are able to store 4 to 5 times more energy in that volume of phase change material, Plentigrade, than we are in the same volume of water. And that's really the process that we're taking advantage of. All we then need to do is find a way of transferring all of that stored energy to your mains water, for your heating and or your hot water and so on and so forth. Now we can dictate where that phase change happens at what temperature. So we have Plentigrade 58, 5, 11, 118, 250. So we can place these thermal storage units at different points within different types of systems, which gives us a lot of flexibility, which is very, very important. And the way you put the energy into these types of materials isn't necessarily important. They're energy agnostic, so you can use heat pumps, you can use solar PV and renewable generation, electricity, waste heat from incineration plants, wherever that energy is and wherever it's perhaps being wasted or it's being generated at particular times of day, it can be used and stored using phase change materials in far more efficiently than you'd find with traditional hot water storage systems. There are other benefits as well, apart from size, the fact that you're not using water anymore, so the Legionella side of it disappears. The fact that we're not pressure vessels anymore, so you can get rid of traditional pressure and temperature relief valves and associated discharge pipe work. So lots of benefits afforded by the use of phase change materials. And we've got rid of those hurdles that Daniel mentioned in terms of cycle stability and so on and so forth. This is the materials these days, you can charge them and discharge them as many times as you like without any loss in performance, with Plentigrade 58 in particular. You can apply the same principles to multiple different sizes. And this just gives an illustration of phase change material versus typical hot water cylinder. I've flown through it a little bit because I wanted to actually move on to some applications of the technology. Now there are various different ways you can input energy into the phase change material, and therefore I'll look at those individually. But if we're looking at direct electric options, then that's the sort of very rudimentary way of load shifting. You're simply charging during off-peak tariffs, for instance, or when there's solar PV being generated, nice and easy, store it in the phase change material for use later on in the day. So the key benefits there: load shifting, off-peak tariffs, increased use of renewable energy generation, and reduce running costs. So really, really easy, and that's probably the most basic form of load shifting that we're going to be looking at. And then we have slightly more complicated examples of using phase change materials. Again, this is more on a domestic scale. On this particular project, the SMILE project, this was on the Orkney Islands, and the Sunamp equipment was used to or be controlled in a smart manner to maximise charging during periods in which the local community-owned wind turbines would otherwise be curtailed by the local DNO, principally due to a lack of demand on the network at particular times of day. So by installing SunAmp to store all of that energy that's generated, it meant we could keep the turbine spinning for longer, and the income generated was therefore increased. So an obvious win. The storage was used to support 30 different homes, and we had different solutions. So you're looking at type 1 here, where we had a combination of heat batteries charged electrically from the energy from the wind turbines, and then we had options whereby, and this was primarily looking at the hot water, and then we had a further type with increased levels of storage, and we were actually using we removed the existing heating system spoilers, replaced it with heat pumps, and looked at load shifting the space heating and hot water as well. You know, for the occupants, they've remained to this day completely oblivious to the operation of these technologies. For them, they still have their heating and the hot water, and they have access to the different energy medias they had before. But they're now also contributing to the revenue generation in the community. So it's been a really successful scheme, and just shows the ability of the storage there to take advantage of energy that's being generated. Project Reheat is another project that we're working on today, and it's up and coming. This is a large-scale technical trial of PCM storage in conjunction with smart controls and heat pumps, Daikin heat pumps. The idea being to reduce the peak demand on the network, and therefore to defer or avoid the sort of network costs that go with that. And also time shift the heat demand so that we could again match the available wind generation in the area, and therefore reduce constraint payments that were being paid in the areas. It's a project with SPEN, or SP Energy Networks, supported by Scottish and Southern Electricity Networks, really with the aim to explore how electricity networks can manage the expected increase in demand created by moving to all electric heating solutions, and trying to do that in the most cost effective and efficient way. And they've identified phase change materials as an absolute pivotal part of that. It's going to be the largest DNO-led scale trial of electrified heat, and will develop technical and commercial solutions that can be rolled out across the country, hopefully. 150 properties, 150 heat pumps, Daikin heat pumps, combined with SunAmp batteries. So as I say, this is an up and coming project, but the potential for it is huge, and we would hope that customers could benefit through lower socialized costs, which would result from saving, these are estimates, but 263 million by 2040, simply by avoiding those network reinforcement costs. And over the same period, we'd be looking for carbon reductions of approximately 1,800 to 1,900 kilotons of carbon by 2040. So a really important project which will provide a template going forward. Other forms of electricity. So I mean, the real advantage of this scheme in particular, and using phase change materials here, the ground source heat pump is really what gives you the excellent coefficient of performance, and obviously the reduced demand on the grid when we're using electricity. But with high-rise blocks, space is a real constraint. And on this particular, this project and many which have been rolled out since, it's really the existence of the phase change material which makes this project even remotely viable. Without it, you would not have been able to install the ground source heat pumps, because there's nowhere for the hot water storage to go. With the phase change material, actually it becomes viable. And not only that, there's no maintenance costs and so on and so forth. So there was the business case to facilitate this, whereas otherwise it may not have been. The last thing I really wanted to talk about was heat networks. There are multiple different generations of heat networks. Generation 1, higher temperatures, obviously probably more prevalent in the USA, or the US, sorry. going down to generation 2 and 3 and 4 obviously being more prevalent in the UK, and obviously 5th generation schemes like that, perhaps more of a future view of that. But I suppose for thermal storage or electrification of the heating and hot water will have a different impact, or a different proportional impact across these different generations of heat networks. Probably more so when we get down to generation 3 and 4, when we start to see the input of renewables more, and air source heat pumps in particular, with the 4th generation. And thermal storage will play a huge part of that in terms of improving the efficiency of the plant, and that could be at the main plant, it could be at substations, at the building level, and also at the apartment or the individual office, and so on and so forth. So, and the beauty of the phase change material is that you have the ability to use different temperature phase transitions to work at different temperatures. So, again, the electrification of heat isn't so relevant at these temperatures. This is more, you're looking at steam. But as we come down to, say, generation 2, slightly lower temperatures, and actually we might see the input of local renewable heat sources coming into play to help mitigate peak demands. That's where we can make use of any renewables that are being generated and improve the efficiency of the system, both on the flow and on the return. And if we're looking at these types of temperature heat networks, then actually we can use some of our higher temperature phase change materials. And it might be that we're working, as I say, different strategies at the different levels of the district heat network sector, whether we're at the main substation, at the building level, using maybe smaller units with a lower temperature plenty grade in, and then at the individual apartment office level, using even smaller storage, and start to take out traditional HIU systems, and start to look at distributed storage, and therefore we can start to deal with overall demands and not peak demands in terms of our individual heating and hot water needs. So as I say, the 3rd generation is where we start to see this is very, very popular or there are lots of these in the UK, not so popular at the moment because of the higher temperatures. So we're all trying to shift towards lower temperatures. But here we've really got the ability to start to use renewable energy sources to take on the peak loads, and that will obviously reduce the demand on the grid. And when we really get to 4th generation and air source heat pumps, that's really where we can start to see obviously the demand on the electrical grid being high, and we can start to lower that considerably by using phase change materials potentially to preheat the water on the return to the central plant, which would be typically a heat pump at these types of temperatures. And by doing that, we can reduce the load on the heat pump. We could even start to reduce the size of the central plant and really start to reduce the impact on the grid. So that's a very quick fly through of all of the different or some of the different applications of thermal storage. I think what's clear is that thermal storage is going to play a key part of it. Phase change materials, the flexibility of them means that actually we're going to be able to be flexible at a time where there's never going to be a one size fits all here. So having that flexibility with the storage is going to be really, really important. Thank you.
Thanks, Toby. I think it's absolutely fascinating, the technologies that are coming through now, and that's why having these sessions is so important, so that everybody can learn about them. So no, absolutely fantastic. Thank you, Toby. So we're going to have a little bit of a shift, and we're going to look at the way that we can mitigate the load, looking at the electrical design now. Ed Sargent from Pivot Power has spent his career working to deliver innovation in energy storage solutions. I will pass over to you, Ed.
Thank you very much, Marianne. I'll start with a little bit about Pivot Power, and then want to give a bit of a background, or I suppose around a snapshot of the battery market, where we are, where things are at the moment. And as Marianne alluded to earlier, and as Toby said, over the last 8 years, the electricity grid has changed, and actually battery technology has changed massively, and is continually in a moment of flux. So there is a lot happening. but it's all moving in the right direction. So it is all very positive. And I'll come on to that a bit. A bit about the background, a bit of Pivot Power to start with. So Pivot Power, in essence, was a battery developer that is now part of EDF Renewables. EDF Renewables are effectively a cousin or a sister company, I suppose, within the EDF group to EDF Energy that supplies us supplies lots of people with electricity and is a standard supplier. The renewable side of things is for EDF Renewables is both initially focused on the wind side of things and now on the solar and really on the larger grid scale. So Pivot's ambitions within that are to develop 2 gigawatts of battery storage over the coming 5-6 years, and hopefully within the next 2 to 3 years we're going to be producing as EDF Renewables another combination of both renewable generation and storage of up to 3 gigawatts coming online onto the system. So ambitious targets for the company ahead, but something that again helps decarbonize the grid. And when we think about it, back to Tony's slide, we peaked coal production in 2012 around the Olympics in this country. So our intensity in terms of carbon emissions was huge, and that's just coming up 10 years ago now. So the shift has been enormous, but there's an enormous amount of way to go. So looking at that, touching on mobility, and of course heat, as has been alluded to here, being one of the largest issues. Often say that when we're talking about e-mobility and the electrification of people with concerns in that space haven't really got their head around the problems we've got with heat coming down the road in comparison. EVs make it look easy. So moving on from that, Pivot's, there we go. Pivot's got a bit of a unique business model. When it launched in 2018, 2019, it was looking at the bigger system. So we actually connect directly into the transmission system. So it's slightly like the motorways of the electrical network. Whereas everything apart from very large steel mills and exceptional factories and generators will connect into the distribution system. So we're actually connecting in one layer above, working more as a some might call it a virtual power plant, but it's at a utility scale. So what I've been really pleased to see is that we kick this off. We're starting to build that national element of lots of 50 megawatt batteries dotted around the country, so in 40 odd locations. And within the first couple of years, we've already seen a doubling of energy density in terms of what we're putting in. So within the same footprint, our first couple that we put in, one in Oxford and one in Kent, was a 50 megawatt hour system, so a C rate of 1. We're now looking at 100 megawatt hours, so the same size system but double the amount of energy stored in it, and that's a really telling sign of where energy storage is going. The other part of the business is to alleviate some of the constraints that have been alluded to here as well, which is looking at providing multiple megawatts to specific businesses. So seeing specifically on EV charging as they ramp up, but we're also looking at some large industrial uses as well, so providing direct power off the transmission system. So bringing something that is a bit of a bottleneck, hopefully within reason, to people that can utilize it better. So capacity is a key point on everything we do, and something I'll be touching on a fair bit in a moment. To just move on to batteries for a moment then, I suppose the last 18 months have been volatile in every way. In batteries especially, we've seen a large shift from a nickel, magnesium, cobalt mixture. They're still used, it's still there for high performance, but in essence, certainly what we've seen in storage is that the LFP, the lithium phosphate mixture, tends to have a slightly better safety record and is in essence less energy dense, so it takes up a larger footprint, but better degradation, so it can be thrashed around a bit more as well. So if anyone in the storage space at the moment in lithium ion is generally working on an LFP basis, certainly at scale. Smaller, maybe smaller compact, maybe domestic elements would stick with NMC simply because they can squeeze it into a smaller space. But again, with more rare earth materials, it comes at a premium. There's been a bit of a shift in the market as well. I spent a couple of years selling energy storage, and it was very easy to sell the sort of 100, 250 kilowatt systems. They were a good size, take up about a car parking space. They're now very difficult to get hold of. And talking around to some of the suppliers, there are very few people or some of the larger names in storage that are actually doing that system size. So sub 100 kilowatts is relatively simple from a domestic point of view. You can bolt together a number of units, and SME level's very easy. Larger scale than that, you're straight into the megawatt size. So you're looking at things that would fit a couple of containers worth, basically. Anything in between is hard to get hold of. Having said that, if you're looking at a portfolio of businesses, there are companies that will definitely look into it at sort of the 500 kilowatt range, or maybe even 250 if there are lots of sites. But I think we will be seeing a resurgence of that in a couple of years, especially as effectively buildings come back online with looking at what the importance is of C&I market and how C&I market could move towards batteries in that size and scale. I think the UK, we don't have a big pull on the global scale of certain industry sectors. Having said that, what we've done with the changes in the distribution pricing around capacity on the electricity market is going to have a big impact on that. So what we come on to in a minute of peak clopping is going to become very important for certain size companies and certain size buildings. On with that, there's lots of announcements in the press about what's being built and the coming online of gigafactories with 40 gigawatt hours a year or 60 gigawatt hours. That is brilliant, and really excited about that. Did I just see in the chat that no one can see my slides?
No, don't worry. Carry on, Ed. You're doing a fantastic job.
Not a problem at all. Trying to rattle through it. That's easy. So on that, the gigafactories coming on, there is a material sourcing issue, not around the rare earth materials. We've had a bit of a glitch in terms of the lithium substrate that effectively makes all the lithium-ion batteries, or is the main material for it. Generally, the pandemic, a lot of mines kind of ramped down, and it's taking a while to get them up, along with a number of other shortages. Some of the leading suppliers haven't moved across. So LG and Samsung haven't moved across to LFP yet. And so effectively everything's coming through one supplier at the moment, which is great for scale, but at the same time is limiting in terms of competition. And there's a couple of other things. Very excited about, I suppose, the Northvolt coming online and potentially Britishvolt as well. For an ESG point of view, if you're focusing on that, they will be the suppliers to go for, because they are focusing heavily on where their supply chain is, what it does, and how where it comes in. There will be a premium price on it, but it will be the best opportunities for you. Finally, I suppose both shipping costs and raw material costs are up over or in the region of 500% in the last 12 to 18 months. So there is a huge amount of cost change happening at the moment in the sector. Again, where we'll see that happening, hopefully with the ramp up of EVs and the scaling up of the gigafactories, it should be good. But in the near term, the next 12, 18 months, it's going to be expensive as we see it. And I think it's the same with a lot of things happening at the moment. So it's not all doom and gloom, I must say. I think these projects don't come quickly. If you are looking at doing them, they do take a long time to prepare for. And this is really what I wanted to touch on, I suppose. If you are looking at a storage project, you need to know a number of things about where it's going to go and what you want it for. And that's probably the key element. Your site, obviously, where you're plugging in and how you're plugging it in is essential. And that'll fit with what you're going to be doing, what the business model for. So your connection to site and the capacity, as I touched on earlier, is in essence your key part. That's without that you can't really start anywhere. You need to know what is your connection in and out. That will depend on really what you're using it for. Your DNO should be able to let you know what you have in terms of adding to that or subtracting for that. Again, wouldn't expect a very quick response. And when a DNO gets in touch or with a budgetary estimate, I would add a fair amount of contingency, because it normally is only a desktop study on that side of things. While considering that EVs are oncoming, look at peak demands, see what is going on with your system, seeing what you know you have in the building already, and what a change of EVs might do. EVs for on-site workplace generally only going to be charging slowly, maximum up to 7 kilowatts, but it's a cumulative effect of those and how many there are. If you're in distribution, then yes, just had a big session actually earlier this week on trucks, and they're now up to looking at megawatt charging standards. So large trucks can absolutely charge at 50, 60, 90 kilowatts if they're going to be in depot. If you're going to be supplying for trucks that are going to be moving quickly, it's going to be potentially up to the megawatt scale. So again, that rolls back to capacity. And I suppose that this, on the HVAC group, this also has a big impact for plant changes. As we alluded to earlier, if you're coming off the gas grid, what impact's that going to have? How are you going to make a change for that, and what does that do to your electrical demand? As I said, the checking with the network operator about what that's going to do, but I'd also heavily check with the supplier about what their future costs or the expected change in costs when you change your capacity are. In April next year, there's a massive change coming in terms of charges from the DNO depending on your capacity. So we're going to see some large step changes, and that will give some accounts departments quite a shock on their bill. If you can add in generation on site, brilliant. If you're adding it with storage, it's a bit of a no-brainer if you're going in for it. Again, very much building shape type will have a big impact on that. There are some massive advancements still being made in PV that will make it interesting, but again, module prices are up at the moment, so I would keep an eye on that one. And finally, just fit. A megawatt, 2 megawatt hour system should fit in a 20-foot container. You'd probably need 2 once you've got the ancillary services and the elements connected to it, and you could scale up from there. So with all that said, I suppose it's what are you looking for a storage system for? Why would you have one? My initial elements of it are looking at self-consumption. What can you do to avoid, if you've got renewables on site, avoid bringing in from the grid as much as possible? And again, this is generally for buildings with an ESG lead, or just a very light use building. If your main usage is just lighting, it's a low rise element, you could put some PV on the roof, you could probably cover it without much. The key to all of this is effectively the energy that you can store, not the power. So on that, you could have a smaller kilowatt system, but you need the longer duration elements. And I wouldn't limit yourself to lithium ion on that basis. There are some really exciting longer duration things coming through. And at the moment on the non-lithium ion sites, government are also throwing money at R&D projects. So early doors would be very interesting to look at. In terms of revenue, if you are up at a decent scale, again, when you get to your DNO, they are looking for flexibility. UKPN in the London region were looking at trying to get 90 megawatts or so of flexibility late last year, and they'll pay for that. It's nothing that you're going to write home about, but it'll help make the project work financially on that side of things. And then again, your sizing of your system can be based so that it covers what you need to when it needs to do it, but the rest of the time it's washing its face. And again, if you can mix in with your renewables, heavily recommend that. The sites for that, even at utility scale, are a bit of a no-brainer. If you can bring it in with buildings, it's an absolute must. So I suppose the real use case here, and has been alluded to in the other presentations, is looking at when you're peak lopping, as we call it, so taking off the tops of when you need it. So here's an example, hot day, the HVAC, as you can see, is taking up a large proportion of the load. So rather than going over your capacity and getting penalised for it, that battery system that's sitting there, working either throughout the year and trading and effectively paying for itself, it can then be used to bring in and cover that difference in the system. It's going to be cheaper than probably looking at either trying to get an upgrade, depending on your DNO, where prices could range for an extra couple of 100k. We've seen prices for 100 extra couple of 100 kVA, prices ranging from sort of 20,000 up to ridiculous numbers in the hundreds and hundreds of thousands. And I saw a 2 megawatt quote for something in the region of 20 million, again, depending on the reinforcements. So definitely consider this, look into that. The battery system can, again, utilize itself throughout the rest of the time, either with self-consumption and or market trading, but really avoid any upgrades that you need to do to either internal transformers, internal kit, and or get capacity from the grid. When sizing that, again, you're looking at long-term usage in terms of storage. So you're probably either going to be coming in with excess power to be able to get the storage or just longer duration. So again, that difference between megawatts and megawatt hours or kilowatts and kilowatt hours is the key to keep an eye on that one. I'm going to finally say a bit of a plug. There are companies out there, EDF are one of them, that will look at all this for you. So we'll come in and do that balance of what can be put in, how can they do it, and what model suits. EDF, not my department, but EDF as well on the renewables department, will do it and almost on a no cost basis. So we'll come in, install a PV system, if there's space, and or a battery where it's utilized, and then sell it back to you on an energy arrangement via just the supplier. You can still have another supplier in there, so it's not going to distribute if you disrupt your current supply arrangements if you're on a group purchasing arrangement. So that's been done on a number of sites, very useful on the larger sheds. And again, the advantage really there, they take a lot of the O&M away and the risk. So stick it with them. It is a longer term arrangement, but if your lease is up for it, it's a no-brainer. And again, I'd also heavily consider this if and when you're looking at plant upgrades. looking at this sort of thing at the same time. If you're going to be having cranes putting new plant on the roof, doing this or looking at certainly looking at what you can utilize in a bigger way would be a bit of a no-brainer. I'm going to leave it there for the moment and take any questions at the end. Thank you very much.
Thanks, Ed. That's great. Sorry about the little interruption in the middle, but
no worries at all.
There's some fantastic things going on there as well. I wonder, I mean, maybe we'll touch on it a bit later, but how the automotive industry and electric vehicles has helped bring the building industry into the right mix. But anyway, we can touch on that a bit later. So closing out the session before our Q&A session, we have Phil Draper. He's the Managing Director of 21 Engineering, and he's the Vice Chair of our HVAC group. He has an extensive history with heat pumps, having led one of the first large-scale retrofits back in 2014. Over to you, Phil.
Brilliant. Thank you very much, Marianne. Just want to confirm this isn't really a plug around heat pumps. What I'm trying to do here is to supplement the information you've been given from the previous speakers. So as much as this might look a little bit of a contrast over looking at some of those peaks and that have been covered before, just to try and give you some sort of real life examples of how electrification actually on existing stock can take place. So I just want to cover a few bits around, basic means, and then give you a few case studies around different types of heat pump installations I've been involved with. So one of the key things, this was mentioned before, really, you just need to get rid of the waste energy. There's an awful lot of heat that's actually wasted in a lot of our properties that can be knocked down. That it actually helps to reduce the peak loads of the heat that's sitting there. I know it was touched on earlier about that very large gas sites. Probably with an effective maintenance program monitoring, that can easily be trapped by sort of 30–40% on its own, just with some proactive management. One of the key things actually around in electrification is model data. What I've got here is an example I was involved with a project. You can see here actually sort of contrast. This building itself currently sits actually with over a 2 megawatt heating capacity sitting at the moment. But you can see here actually with some CO2 and actually allowing some sort of drift actually on the peak loads for heating, we can get it somewhere down to a megawatt. One of the key things around electrification for heating is domestic water. You don't really want the tail wagging the dog. Most of the year round you need to get a higher 60+ temperature actually for domestic water. Most of the time space temperature doesn't need anywhere near that. I'm not going to start the argument now over what actually temperatures should go on and actually resizing of rads and coils and open pieces. But one of the key requirements is to try and get that domestic water off to not having to overheat spaces. I do suggest any projects you are looking at going with around electrification, engage straight with the manufacturers. A lot of these guys know their equipment far better, as you'd expect, than what a lot of the consultants do. And I include myself there. I engage an awful lot with some of the big guys, the Dakins, Mitsubishis, Clivettes, those guys. And they help me actually decide which solutions are viable for my clients from the early doors. The key thing actually to make any of this work, and probably actually some of the points moving with the peak loads, really is around the controls. Without an effective control system, possibly interacting with CO2 points here, electrification won't work, and you'll probably end up reverting back to a gasless system for ease of use. So this system here is one that I recently got involved with, sort of a brainchild for myself sort of 3 or 4 years ago. What we've actually got here is something that doesn't generally work very well. I'm told quite a lot. We've actually got heat pumps acting in line with the boiler system. So what we're able to do here, and you can see with an outside air temperature of 7.6 from the other day, the heat pumps themselves are picking up the loads and operating the building. What would actually happen here if we needed a higher temperature, we'd still control to a suitable return of sort of 45–50. The heat pumps to give us 5 degrees, and actually the boilers would actually top up. This system here actually is a mix between FCUs and VAVs, and we completed it last year. Here's just a sort of a quick graph actually over the savings, give you an idea actually what gas reductions can make here. You can see actually in 2018, again I've gone pre-COVID, this building was using on a similar outside air temperature 905 meters cubed of gas in a day. We've now got it down to 50, dramatic change. You all know here the very large increase in electrical consumption. Again, you've got to get the usage from somewhere else. We do expect this project here to achieve a sort of 95% at full gas reduction once we've fully commissioned the building. Here we've got a variable temperature system, not probably as you'd expect it. What we actually had here was 2 gas-driven modules on the AHUs. The gas units are still in place, but what we've actually done here is converted the cooling coil to actually operate as a variable temperature. So we replaced 2 of the Johnson's chillers that were on the roof and put in a Daikin heat recovery unit. At this point, then we're able to give 50 degrees through the cooling coil to make it a heating coil. Again, this one is a fan coil system, completed last year. And now I'll show you one of the graphs. Again, looking back to a 2018 data, we was using 250 cubic meters a day. We're now down to 13, and that actually is for domestic hot water. But do notice here, actually, due to the nature of the building, quite a highly glazed building, we're actually using less electricity than it was before. To a degree, actually removing some of those peaks actually were in place before. This project here was completed in 2014. One of my love childs around heat pumps. I could talk about this all day, I'll try not to. This actually is an EVA system. Unfortunately, we're not able to operate the boilers with the heat pump due to the makes of the boilers. But what we are able to do is actually operate on a pre-warm scenario. So what we need is a higher temperature for the largely glazed building here. We can actually use the boilers to get the system up to temperature, and actually when the loads are there, building's warm using the heat recovery, and we've got the aspect over people, the heat pump can actually kick in. And again, this has been going since 2014, so we've got some good knowledge on how these work. And what I'm going to touch on here is some of the reductions. You can see here that from 2013 that we was using 400 cubic meters of gas a day with an outside air temperature of sort of 4 or 5. And actually now a graph from just last Thursday that we're actually using 0 amount of gas and actually, again, a lower electrical consumption. And just to sort of touch on some of the numbers, actually what can be done here, trying to, again, remove the myths around the cost of the doing heat pumps and how they don't pay for themselves. This job actually had a capital cost of £800,000, and since 2013, using sort of the amortised numbers, we're actually tracking over £800,000 savings since that date, which actually has covered the capital cost of itself in 7 years. I'm not going to delve too much into it. This is a solution I put forward to a client recently around a mixed-use system, currently operating actually with 6 megawatts of boilers. What we're going to try and do here is remove the need for any direct boiler replacements, reducing the temperature lines. Unfortunately, we can't get rid of the high temperature needs for residential, those bits and pieces, but this actually then takes away the need to actually have such a high peak load. Currently, we sit around 2-3 megawatts, and this actually take it down to an awful lot. That was very short and sweet, but just to give you an idea of where it sits and just to give you some confidence that electrification in buildings can take place.
Great, thank you so much, Phil. So we have had a few questions that have come through, so I'm going to attempt to relay these to our speakers and see if we can get some discussion going. So the first one I think is directed at Daniel, and it's from Colin Ashford, and his question is, for thermal energy storage, is it possible to note the maximum rates of discharge and storage needed if charging from, say, off-peak electricity? So e.g. Octopus Go with 4-hour rate availability.
I think, can I share my screen?
Yes, please.
Presentation? Can you see that?
Yep, that's coming on now.
So this is a reference to the paper actually that Steve talks about, but this is a PCM system which we tested. In regards to power inputs and outputs, this is the sort of input power, the peak input power we got, and it does deteriorate with time, but it does give you an idea of roughly how much power you can put into the system and then roughly how much power you can get back out of the system. So yeah, but like I said in the presentation, most of these thermal systems are really quite scalable. So obviously you're unlikely to get 30 kilowatts of input power, but that can be scaled down and you can get a lower power input for a longer duration time. If that answers the question.
Yeah, thank you for that, Daniel. I've got one for Tony. is using direct electric to heat the thermal stores viable in the medium to long term for grid stability, given that it does not really reduce the 4 times larger heat demand of GB versus grid capacity?
Yeah, and that's from Chris, isn't it?
Yes, that's from Chris.
So yeah, I mean, I've always been reluctant to suggest you should use direct electric heating anyway. From a purely exergy point of view, this is a bad use of very high value energy to have what's considered a very low value energy form, which is heat. So in the hierarchy of things, you should use electricity for higher value end uses such as lighting and motive power and all the rest of it. But yes, you're right, Chris, that doesn't help us a great deal. It does help to shift the load, but it doesn't help with the energy efficiency of the entire system, and that's why heat pumps is a game changer in terms of that. And heat pumps with energy storage starts to really help improve the overall system efficiencies and system management.
Thanks, Tony. Did anybody else want to come in on that as well? No, that's fine. I will accept your answer, Tony. Hopefully, Chris, you are satisfied with that. We have Chris on the line, so at any point he could unmute and ask a question as well. So I'm going to now direct a question at Toby. For the phase change materials, what are the lower operating temperatures, and how well do you think they work with the heat pumps with 50-degree outputs?
Well, at the moment, we're actually in the process of developing a phase change material, which has a transition temperature at 50 degrees. Hopefully that'll be ready later on this year, and that would be targeting the lower temperature heat pump temperatures. But as I say, at the moment, PCM58 is the predominant phase change material that we're using with heat pumps, but we have temperatures 5 degrees, 11 degrees, even 118 degrees or 250 degrees. So we have quite an array of temperatures available. But at that lower heat pump temperature where it's still suitable for hot water, so i.e. a sort of a 50-degree mark, that's actually in development now.
Okay, great. Can I just ask our presenters to turn on their cameras as well, just so that the audience can see when you reply, if that's okay. Great, thank you. Thanks, Toby. So it does look like there is some work out there that's going to help with those temperatures, because there was a couple of questions on temperature. Ed, I've got one for you. Are there any technologies coming out that will align charging with reference to the grid loads?
Align charging in terms of, okay, so in essence, i.e. looking at pulling energy into a system depending on what's grid doing.
Yeah,
I think, to be honest, the simplest one at the moment is the simplest example of that is probably just the Oxford Octopus Agile Tariff. As a point of reference, I'd say that's you're there. Slightly depends on what grid load you want, whether it's a cost-based grid load or intensity. You can get the data straight off it. There are some apps that people are developing to say actually the grid's doing this, but most people are actually working off carbon intensity at the moment. So we saw over COP number 10 had a green arch if the carbon intensity was low. Didn't actually put any numbers on it, but lower than yesterday for sort of thing. So I'd say that more people are doing it around carbon intensity at the moment. If you're doing it on a pricing basis, yes, lots of people are doing that, but again, will depend very much on your structure of your energy supplier and how they're doing it.
Okay, thank you, Ed. Did anybody else want to touch on that one? No, that's fine. It was for Ed. Okay, right, I'm going to go back to Daniel. I've got a question here from is it Melinda Homewood? And she's asked, is there a consensus on whether energy storage, that's batteries or thermal storage, is more effective on an asset level or on a district heating level, on a district level? When we specify solar PVs on a building, should we also be specifying some form of storage at the building, or should we be exporting it to the grid? And really, should the grid have larger storage systems?
I can't really speak to the finances directly of each of the systems, but the issue with electrical systems, you could have a large battery installation off-site somewhere on the grid connected, but with thermal energy storage systems, really they need to be local because the transportation of heat can just encounter quite a lot of losses. So you could have local small district heating networks where you can transport the heat locally, but sending heat back to the grid and forwards is just going to encounter quite a lot of losses and make it not very feasible. Whereas electricity, obviously, we can transport it very long distances with minimal losses.
Anyone else wants to? Toby was there. Did you want to add to that one? Don't worry. If not,
that answers it quite well, to be honest. I suppose that the thermal storage is right. You use it on a local level, and if you're, I suppose, the price comparative, battery charging for electricity is slightly more expensive than thermal storage at this moment in time, but it's not going to be an either or. Generally, there's going to be a combination of both sets of types of storage in most situations.
Thank you. So I've got another question for you, Toby. It's could the phase change be used as part of a normal LTHW system? And as I suppose, I'm not sure whether this is a boost, giving a higher grade heat in winter mornings when the outside temperatures are lower than 5 degrees and when heat pumps are normally struggling.
Yes, the only benefit of doing that would be, well, yes, there's no reason you couldn't do that. I suppose you'd have to have a view of how you would be, what the primary energy source of the thermal store would be. You know, if you've got some solar PV available, perfect. And then you've got, if you're using PCM 58, for instance, you would have circa 55 degrees available to top up the heat from the heat pump. That wouldn't be too much of an issue. You could even do it with off-peak grid electricity, but it's not as efficient. Obviously, it doesn't have the COPs of the heat pump if you're doing that.
Sure.
But it certainly can be used as a boost.
Phil, I wasn't sure if you were going to jump in there. You look like you're about to say something. And you're on mute, so we can't hear you.
That was my question, but I just tried to make it.
Oh, there we go. Does it answer your question then, Phil?
It does, yeah. So obviously, one of my units there from 2014, we have to run the boilers an awful lot more. So potentially, actually using one of those could be quite a cost-effective way of using the older heat pump technology rather than actually replacing it.
Yeah, I think that's
from the moderators there.
Yeah, I think there's going to be a little bit of that. I mean, also there's all sorts of interim solutions that we can work with. I mean, it may be that there's gas combis everywhere, aren't there? You could use any PV that's being generated, that's being exported to the grid at this moment in time, use that to charge and create some thermal storage, and then use the thermal storage as preheat to the combis to displace a lot of the gas consumption. So that might be, that's just a way of utilising generation that's already there, and could be it's a much cheaper solution than necessarily jumping straight to heat pumps, which is inevitably where we'll all get to at some point in the future, I'm sure.
Obviously, we need to try and avoid, utility costs has doubled effectively as it is, but I think we need to try and concentrate on moving towards a net zero aspect. Gas is becoming a bit of a dirty word. And, as Tony picked up, we can't cope directly with just moving everything over to electric. So it doesn't actually come down to a PV aspect, but where the grid has got a spare capacity from wind or hydro over it sits actually 2, 3, 4 o'clock in the morning, if we can use electrification to boost the temperature through your sort of technology and release that actually later in the day to reduce that peak aspect, then it allows and to work with the technology like Ed was saying with the batteries, allows everything to sort of work more in tandem with each other.
Absolutely, yeah.
Thanks. We got a couple of other questions that have come in. Tony's actually asked one of Ed, so I'm going to ask you this question and then you can tell Tony off if you don't like it. So what is the state of play for flow batteries? In theory, these can provide lower cost energy storage.
Yep. No, great question, and very topical. We've just installed a 2 megawatt, 5 megawatt hour Vanadium flow system on the Oxford project. So your commission for the question will be coming later. On that basis, they can. Currently, their round trip efficiency is not amazing in comparison. So you're losing 20% odd more than lithium ion in terms of their round trip efficiency. We found the degradation is amazing in the sense that it'll last a lot longer because it's all mechanical, but we have got issues at the moment with the materials. Vanadium is very expensive, so getting that working right, it is certainly part of the tool chest in terms of energy storage. Whether vanadium flow is the right materials or there's developments and we'll look back on it and go, oh, that was one of those systems, I don't know yet. All for the longer duration, we definitely need it. Its energy density is quite low as well. It does take up quite a lot of space in comparison, so it is large. But yeah, if you're interested in it, absolutely swing by Oxford substation. We can go and have a look at a system together, just going live at the moment. So very keen on it myself. It hasn't got a lot going for it, hence it's not being rolled out hugely at the moment. Fingers crossed for a breakthrough soon.
Sorry, Ed, I don't know if I'm the only person in the audience that doesn't know what a flow battery is. Yeah,
so in essence, it's very simply put, it's a mechanical system. So not dissimilar in a way, I'd say, to a heat pump. Tony will probably jump on me for that, but it's the transfer of material from effectively one tank to the other and back again, changing state on the way through.
Okay, great. That makes sense. Lovely. Thank you very much for that.
No worries. I can't tell you that much more about Vanadium other than it's called Vanadium, to be honest, and it's bloody expensive. Very expensive, sorry. I'll leave that one as well.
Lovely. Right. OK, so there is a couple more. Trevor James has asked, recovering otherwise waste would be the first port of call. How can heat pumps with thermal storage take advantage of this particularly grey water energy? I'm going to direct this at Phil.
Is that what I should have been listening then? Sorry, I wasn't reading the questions that came in.
Recovering otherwise waste would be the first port of call. How can heat pumps with thermal storage take advantage of basically waste water?
Yeah,
grey water.
The hard bit with grey water, again, it's trying to get that time period. I'm assuming grey water here is rainwater or cooling towers, effectively, it's been pre-used. You could actually put turbines effectively on a downward pipe and actually get water going for that way. I did engage with a manufacturer 6-7 years ago around that one. The issue you've got then is a continuation of the water going down. We do regard the UK as quite a wet country, but we don't have the continual water going down to driving a turbine in parallel. You could put it on cooling towers have an awful lot of sort of drop down in terms of actually dumping for water, but again, it's not continuation. So there are means actually of recovering the water to turn into a fuel source. I know actually in Scotland, actually, I think they've got a hydro plant that actually then charges and pumps the water back up at night. So you could sort of utilise that sort of technology, but it wouldn't be very cost effective actually on a sort of a small scale points that we normally see somewhere actually on a commercial building.
Yeah, I think recovering waste is an interesting one, and I'm not sure we've got it yet. But I think
I might just add to that. I did come across a project with a chap who's I think it's ESB or GI Energy. Anyway, they were putting collector coils in the effluence pipes of a large tourist attraction, because they realized that it was a very old site and the pipes were big enough to walk down, but they could get effectively a constant 25 degrees or 20 odd degrees in that section of the building. So a bit of a crappy install, excuse the pun, but something that they did actually utilise from the waste heat because the site was open 360 days a year and it was a constant temperature down there because of its depth and its thing. So I think innovative things like that, there is use for it. You might have to think outside the box.
Yeah, and that's what we're having to do increasingly. So I think that was a good example. Thanks for that, Ed. I'm actually going to make this the last question. Our attendance is dropping, so let's ask. Andy's got a bit of a concern, I suppose, with all the high-tech systems and many components and complexities. Do we think that there is at present enough operational data available to determine realistic in-use predicted costs for maintenance? So ongoing, so staff, resource, consumables, etc. For the expected lifetime of the systems that we're putting forward, including decommissioning and disposal. And I will put that out to anybody.
I can talk to a little bit if you like. I think I'm not, from the electrical battery side, I'm not an expert, but from the thermal side, typically the thermal systems are relatively simple. They don't have too many components, not very many moving parts. So for example, a phase change system is simply a block with a heat exchanger inside and a lot of a PCM material, which can be typically like a wax, like a paraffin wax or something like that. So obviously you've got a pump, but that's external from the phase change system itself. There's no real reason, as long as it's sealed correctly, it can have many cycles without needing much maintenance at all. And that's kind of the same for thermochemical systems as well. And actually the materials in a lot of the thermochemical systems for domestic use are relatively safe. A lot of the work looks at magnesium sulfate, which is bath salts basically. It's widely available, non-toxic, low cost, has a very large energy density. We just need the systems to be rolled out. Yeah, so thermal energy storage systems really, they're not, like I said, there isn't many moving parts and they should require minimal maintenance. And we've run, especially for PCM systems, many cycles in the lab with consistent energy outputs. And I'm sure Toby has similar experience with the SunAmp systems.
Yeah, if I could add to that, Daniel's absolutely right. I mean, we use a particular material, sodium acetate, which is salt and vinegar. It is readily available. It's a sustainable material. It's non-toxic, non-corrosive. But so in terms of the afterlife side of it, it could be repurposed and reused as de-icer if needs be, or even used in further technologies. But I suppose it's also designed so that you can use it as many times as you like without it losing performance. But in terms of the maintenance side of it, as Daniel pointed out, there are no mechanical parts in play here. It's just a heat exchanger. And for that reason, at SunAmp, we actually provide a 10-year warranty on the unit, and that isn't impacted by a lack of maintenance. So it really is a fit and forget item. So for us, I showed the project earlier with the ground source heat pumps. With that particular project was Kenza shoeboxes, and internally within each of the apartments, with the shoebox and the SunAmp battery, there was no maintenance or access requirements. So for social landlords, it was an absolute winner. Really, you could save them an absolute fortune. Anything that and outside of the properties, it was a simple pump. Sending an ambient loop round, so no heat losses outside of the individual apartments. All the temperature increase came within the property. So, yeah, these systems very much designed around lack of maintenance, efficiency, and in the most, certainly in SunAmp's case, very much in terms of a whole life cycle approach to it.
Thank you. I think that was a very comprehensive answer. So that's great. Now I am actually going to round up the session. What I would like to say is thank you very much to our speakers, to Tony.
Just Tony.
Marianne, you got on mute.
You went on mute. I thank Tony as well. I'm not going to.
I think. Did I go on mute? Myself. Did it? Was I halfway through the conversation?
Oh, sorry.
Oh, there's. I think it's the wind outside. I can hear it howling, and it just. So who did I not thank?
You just thanked Tony time and time.
Oh, okay. Well, that's sorry about that, guys. Yeah, sorry. Ed, thank you. I went through the whole name. Daniel, Toby, and Phil. And Chris for helping out, and Matt in the earlier AGM. So it's been a fantastic session. Thank you so much, really informative. The session has been recorded, so anybody that missed the latter end of it or missed it altogether will be able to see it, because we'll post it on our LinkedIn, I think, page. And someone's apologising because they turned me off. I get the picture, you want me gone. But thank you everybody for attending, and we hope to see you at the next session, which will be, have we got a date for it, did we say?
18th of May.
18th of May, lovely. Thank you so much. Bye-bye.